Okay, hello again, folks. Welcome to another rousing edition of Digestion Videos, Biology 12. We talked in the last video about enzymes in general. What I want to do in this lesson, it's kind of short and sweet, although it is going to take some time to digest it. Zing. That was so funny, Heinrich. I threw up in my mouth a little bit. Sorry, bad joke. It is kind of short, but you need to know all the different enzymes that are involved in breaking down carbs and proteins and lipids. And it turns out the list isn't incredibly long. Let's just jump right into it. So 331, what the heck does that mean? That means there are 3 enzymes that are responsible for breaking down carbohydrates, taking carbs from long chain starches down into single monomers of glucose. There are 3 enzymes that break down proteins. Remember, polypeptides are like 50 plus amino acids all joined together, and we cut them down into smaller and smaller pieces until we get into individual monomers, which were amino acids. It takes 3 enzymes to do that. And there's only 1 enzyme that breaks lipids down. So remember, lipids are made out of 3 fatty acids and a glycerol. It only takes one enzyme to break that down. So in terms of carbohydrate digestion, we know there's 3 of them. We've already talked about one of them anyways, if you remember from the very first lesson. What we're doing for the first step in carbohydrate digestion is taking starch. That's this picture right here. And we're going to break it down into maltose. So we're going to cleave some bonds through chemical reactions, some help with those enzymes, active sites, all that good stuff that we talked about. These will be hydrolysis reactions that release water. We're going to turn starch into maltose, and it turns out there's actually 2 enzymes that do exactly the same job. The first one, you may recall, works in your mouth. Hydrolysis just means the breakdown. So the breakdown of starch into maltose, so this long chain, this would even be a longer chain, it's just showing 4, but breaks it down into these sections of 2. This is a maltose sugar. The first enzyme that's doing that in your mouth is salivary amylase. And you might remember that's the one we said is produced by your salivary glands. So in your mouth, you're chewing things, you've got some mechanical digestion happening to increase the surface area. And then you have salivary amylase produced by the salivary glands, which starts breaking down any starch into maltose. And you may remember the video about my strange brother swallowing pierogies whole. And you might think to yourself, well, you're not really going to have a lot of starch digestion happening in his mouth then. And pierogies are nice and starchy. Are you going to be able to digest the pierogies then? And the answer is, well, you don't have an optimal surface area because you didn't really mechanically digest it. But there is, oh sorry, I should throw that in there, pH of 7-8. Your mouth is about a neutral pH. In your small intestine, by the time the starch gets there, there's actually nothing in your stomach to break the carbohydrates down. So it passes through undigested in terms of carbohydrate anyway. In the small intestine, you have exactly the same reaction, the hydrolysis of starch down into maltose by something called pancreatic amylase instead of salivary amylase. And the names are kind of nice. The salivary amylase was produced in your salivary glands, and the pancreatic amylase, as you can guess, is produced in your pancreas. And then it travels through a little duct into your small intestine, and it's actually doing the same job as the salivary amylase. So we've got a bit of redundancy here. Just means that we're definitely going to have, either in your mouth or in your small intestine, or very likely in both spots, all of the starch broken down into maltose. So that's 2 of the 3 enzymes, and now we have to get the maltose right down into glucose, into the individual monomer. pH of your small intestine, sorry I keep forgetting about pH, it's about 8, right? It's really close to neutral. So carbohydrate digestion is 2/3 of the way done already. Let's finish it off. How do we go from maltose into good old glucose which we can then use for cellular respiration. Been there, done that. The hydrolysis of maltose down into individual glucose sugars is done by an enzyme called maltase. That happens in your small intestine, and the maltase is produced by your small intestine. So these words in italics here after the enzyme, that is showing you where that enzyme is actually produced. So that enzyme is produced by your small intestine, it works in your small intestine, and we break the glucose right down, or sorry, the maltose right down into glucose. And then we'll see in the next lesson that that glucose travels in the bloodstream, gets absorbed by the small intestine into the bloodstream, travels through your bloodstream to your liver, and then the glucose, with the help of insulin, is going to be stored. So that is carbohydrate digestion. We're done. So salivary amylase, pancreatic amylase, turning starch into maltose, and then maltose into glucose by maltase. So there you go. Carbs, done. What about proteins? So we take big, long polypeptides, huge, long chains, 50 plus amino acids, and we break them into peptides, which are just think about it as really long chains into smaller segments. The first place, you may remember this discussion as well, was your stomach. Stomach was kind of funky. It's the only acidic spot in your entire digestive system. So when I was throwing those pH values in there and forgetting about them, really they're all going to be about neutral, 7 or 8, except for your stomach. So remember, the hydrochloric acid is very acidic. It's pH 1 to 2-ish, something like that. The hydrochloric acid is going to help denature the protein, which sort of opens up the chain. Doesn't cut the chain yet, but it unwinds the three-dimensional shape, which is kind of like unwinding something and making it easier to cut up. And that's what the enzymes are going to do. They're going to start to hydrolyze, to break down that really long chain of proteins. And the first one is pepsin. And recall that hydrochloric acid has a really important job in that it activates pepsinogen, which is the inactive form of pepsin, into its active form, which we then call pepsin. So this is actually the enzyme that is doing the breakdown of the proteins. The pepsinogen is simply the inactive form of that enzyme, and the hydrochloric acid is the person who's actually making it active. They're like the person who goes and flips that light switch. So hydrochloric acid is not an enzyme. Pepsinogen is an inactive enzyme, and then pepsin is the actual active enzyme form that you'll want to know. And there you go. Pepsin takes the big long chains, 50 plus amino acids, polypeptides, cuts them into peptides, which are going to be less than 50 amino acids, but still fairly long chunks of amino acids. So that's the first sort of cutting. This happens in multiple steps. Protein digestion, we then take those polypeptides and we cut them into shorter pieces. Now we're into the small intestine, right through the pyloric sphincter into the small intestine. The peptides get cut into smaller pieces. The next enzyme up is called trypsin. Trypsin is produced in the pancreas, but acts in the small intestine. So it breaks the peptides down into smaller peptides, and then the small peptides get chopped up right into the individual monomers, the amino acids, by enzymes called peptidases. Peptidases are produced in the small intestine, and we're still functioning here in the small intestine. So for protein digestion, if we think about the 3 enzymes required, it was pepsin, and then trypsin, and then these peptidases. The pepsin worked in the stomach, and the trypsin and peptidases produced in different places, as you can see here, but they work in the small intestine. That gets us down to amino acids. Our body then takes in those amino acids and uses them to rebuild more proteins, more enzymes, whatever our body needs. Now, lipid digestion, this was only one enzyme, although there's actually 2 players. It turns out that, kind of like in your stomach, how hydrochloric acid wasn't an enzyme, but it was a player, we have something similar going on with lipid digestion. And that is bile. which some people have actually been asking about already. So lipid digestion occurs only in the small intestine. Doesn't occur in your mouth, doesn't occur in your stomach, just in the small intestine. The first player, this is not an enzyme, but the first player is bile. Bile is made by your liver. It's stored in your gallbladder. And then when you are digesting food, your gallbladder squeezes that bile into your small intestine, and it is going to physically break fat into smaller droplets. And that process is called emulsification. This word right here. That is actually the same thing that soap does. When you use soap to break down or wash like grease off your hands, what it's doing is it is actually made up of kind of phospholipids, and they surround this big chunk of lipid here that you can see, and they break it up into these smaller pieces, and they form these little hydrophobic circles around it. We break it down into smaller pieces. So when you're washing your hands with soap, the soap emulsifies anything that's fatty, surrounds it in these hydrophobic circular sort of baskets, and then you wash it off down the sink. Here we break the big chunks of fat into smaller chunks of fat. And why would we want to do that? Because we want to increase the surface area for the actual enzyme that shows up next to do its job and break those fatty droplets down into individual fatty acids and glycerol. So the actual enzyme, after bile, physically breaks the lipid into smaller pieces. The actual enzyme that does the breakdown of the lipid into glycerol and 1, 2, 3 fatty acids. This happens in the small intestine. The enzyme is lipase. And that's produced in your pancreas, but it works in the small intestine. Remember that the pancreas, food doesn't actually pass by the pancreas. It's an accessory organ, and it's adding some special things like these enzymes that we've talked about through a little duct, through a little tube, which travels to the small intestine. So that's the lipid digestion piece. Bile, which is not an enzyme, physically breaks it into smaller pieces, and then lipase from the pancreas actually does the hydrolysis, real chemical breakdown into the individual monomers. I should go back to bile for a moment if I can here. If you've ever had a family member with their gallbladder removed, my mother-in-law had hers removed, that means she doesn't have very much bile being produced in her digestive system because it doesn't have this nice little storage facility where it can be squeezed from every time you eat. So she's just fine, but she has a little bit of sensitivity now with fattier foods, which is to be expected, right? She doesn't have bile breaking the big droplets of fat into smaller droplets to increase the surface area for lipase, so her body is having a tougher time breaking down those lipids. And if she eats a really fatty meal, like some really rich pasta sauce or something like that, sometimes that can actually irritate her bowels, her large intestine, and it can cause things like diarrhea. So if you're ever thinking about the sort of what would cause irritation in the large intestine, it could be like a bacteria or a virus. It could be something like this. It could be like lipid pieces that are too large that weren't completely digested. Small intestine, there we go. So that's actually all three. So there's not a ton going on, although you do have to figure out sort of what the enzymes are, where they were produced, and what they're actually doing. So for carbs, remember there was salivary amylase, pancreatic amylase. They did the same job, starch into maltose, and then maltase, breaking down the maltose into individual glucose. Proteins, you can see there I put hydrochloric acid in brackets because it's not actually an enzyme. Pepsin, trypsin, and peptidases. That's the order of those. Those are actual enzymes. And then for lipids, bile in brackets because it's not actually a digestive enzyme, but the lipase is. The bile is just helping increase that surface area. There you go. This is the song Cotton Eye Joe. I Can't remember the band's name. Sorry, I should know this. But in Cotton Eye Joe, if you've heard that song, where did you come from? Where do you go? And in addition to the names of these enzymes, you're going to need to know where do they come from. That means where are they produced? And then where do they go? That means where is their site of action? Where are they actually doing their thing? Oh yeah, there you go. Where did you come from? Where did you go? Where did you come from, Cotton Eye Joe? Sorry. So you kind of need to know this list. Notice there is nucleic acid digestion. I'm not going to worry about that one. It's here in this picture for your perusal. You'll get that answer right on Jeopardy. But it's really the carbs, the proteins, and the fats, the lipids that I need you to know. So you need to know where they come from, where are those enzymes produced, where do they go, where do they actually work, and the pH level is not a huge deal. I want you to think most of them are neutral or slightly basic. The only exception, this one right here. This is the special case, the pepsin in your stomach, which is incredibly acidic. The rest are working in your mouth, pH 7 or 8, or the small intestine, which is pH of about 8. So pretty darn close to neutral. So that is the stuff you're going to need to know. The practice that goes with this is going to be this document right here. So this is just on the website towards the bottom. Digestive enzymes, what I need to know, so you can complete this table. Again, it's listing the enzymes, where are they produced, where do they work, and they turn this thing into this thing. So for example, carbohydrates, number 1, salivary amylase. Site of production, salivary glands. Where does it work? Where's the site of action? Mouth. It turns starch into maltose. So that would be like your first line there. There are some additional questions at the bottom here. What can you tell me about pepsinogen? What can you tell me about bile? I won't answer those questions quite yet. Check into a Zoom meeting if you'd like the answers. So give that a try. Bring any questions to the next Zoom meeting or hit me up with an email. I'd be happy to help. Have fun learning about and perfecting your knowledge of digestive enzymes.